It seems not to be started yet. Okay, it seems that now it's started the webinar. Hello, everybody. Good afternoon to most of you, or good morning, depending on where you are. It's really nice to be here today to present this webinar. So today we will be talking about a beam shaping system, which is providing a ring shape for laser beam welding working up to 16 kilowatts. And I'm glad to present this webinar today with Mathieu and Nicolas.
Hi.
Hi, hello.
So Mathieu and I, we are working at Cailabs. So we have worked on the beam shaping part, and Nicolas is working at the Institut Maupertuis. He has worked on all the process results. So actually on the bottom right of your screen, you can see a chat. So if you have any technical issue hearing us or whatever technical issue you would have, do write a message there. We have Clementine who is also following the webinar, and she will be able to help you in any issue you would have. You can also ask the questions you have in the chat. At the end of the presentation, we will have a Q&A session, and we will go through all the questions that you have regarding the three presentations. So what will we discuss today? Well, we will start by having a look at the challenges that we want to tackle with the beam shaping system that we have provided, and more specifically, the laser beam welding challenges. Then we will describe in detail the solution that we have provided to the Institut Maupertuis, and we will get into all the technical performance of the system. We will then go through all the process tests that were done at the Institut Maupertuis, and we will conclude by summarizing all this and looking at what are the next steps of all these developments. Please, let me start with a few words about Cailabs. Cailabs, we are a French company based in west of France, and basically we develop, manufacture, and sell beam shaping systems. Whatever we are doing is related to MPLC, which stands for multiplane light conversion. It's a new, unique way to do beam shaping. It has been patented from the beginning, and actually we have partners all over the world working with our systems. In the last few years, we managed to raise nearly 17 million euros, which on one hand enabled us to hire a lot of talented people, and which also enabled us to develop ourselves with a lot of different partners on a lot of different applications. But what actually is MPLC? Multiplane light conversion is actually a unique technology to perform beam shaping through actually propagation through a succession of multiple faceplates. As you can see on the bottom left on your picture, you have a lot of different faceplates. The light is going through all those faceplates, and at the end, you manage to get the shape that you want. This is the initial way we implemented that many years ago now. On the way, we realized that it was much more convenient to develop an MPLC with reflective optics. So now we have two mirrors. We have the light going back and forward, both mirrors. One of the mirror is textured, and that actually enabled us to perform the beam transformation and the beam shaping. All this, as you can see, is actually passive and is definitely reflective, which actually enabled us to handle high energy and high power. This is really important for what we are doing related to laser beam welding. We can have multiple beam as the input or at the output. The system you see in the picture in the middle is an actual MPLC, but it's pretty far away from what we will be discussing today because it's a system made for telecommunication. So where do we use this MPLC? Well, actually, we managed to use our technology in a lot of different applications. We have done a lot of telecommunication application. Aruna is made for local network improvement. Proteus is made for laboratories. And Tilba is made for communication in between ground and satellite or satellite to satellite. It's actually laser communication. In our custom product line, we have as well developed system for defense or for medical application. But today, we are here to talk about laser material processing. We want to apply MPLC and beam shaping to all the material processing that exists with laser, and we want to improve those processes with our products. So what exactly is CANUNDA today? I will be very short on that. We have three types of systems which are dedicated to pulse laser. We have Canunda Pulse, Canunda Axican, and Canunda Split. It's actually the systems that you can see on the bottom of the image, the black boxes, and the small optics, which is gold-coated. But this is not why we are here today. We are here today to discuss about CANUNDA-HP. It's our product line dedicated to high-power, multi-kilowatt CW laser. It's actually the system you can see on the back of the image with all the wires and all that. So the idea of this system is to handle a lot of different processes, but always handling multi-kilowatt CW laser. What exactly can we do? Well, we try to work on all the application of material processing with those kind of laser. It can be laser cutting, laser welding, additive manufacturing, composite heating, or surface texturing. And as most of you know, all those applications can be related to a lot of different type of end users on a lot of different industry. What do we want to do exactly? Well, related to all those processes, we know actually that beam shaping can improve the yield and the quality of the processes. But depending on the process, that's not exactly the same shape that you want, and that's not exactly the same type of improvement that you will have. Here you can see a few examples of typical shapes that can be used for laser beam welding, for laser cutting, or for additive manufacturing, which are actually very different. In each cases, you see that the process improvements are very different, but you always find a way to improve the process with beam shaping. What do we do exactly in our systems? Well, we try to have, first of all, the optimum shape. When you have a specific process, you need a specific shape to have the optimal process. And we can do any kind of shape, symmetric, asymmetric, complex, or simple. In any cases, we try to always to preserve the depth of field. It's very important to have a high depth of field if you want to have a robust process. Also, in all the systems that we develop, we try to handle high power. We have proved already that we can work up to 16 kilowatt, but we are not afraid with higher power than that. And in any cases, we also try always to have a reduced focus shift. Focus shift is actually what you have when you heat up, when you have a lot of kilowatt going inside your system. The lenses that you could have inside will actually heat up, thermalize, and their focal length will change, and you will have the focus plane which will change over time. We Cailabs, we try to always have a minimum reduced focus shift for having a stable process. At last, when we develop our systems, we always try to think about the industrial environment in which it has to be integrated. We want to have systems which are compatible with all the equipment that you will have. It can be the scanners, it can be the laser that you have, but we also try to be compatible with robot arm as well as with machines such as additive manufacturing machines, for example. Now we will have a short survey. So it's time for you to work in this presentation. And actually, I will ask you a question if you have already used beam shaping to improve your processes. So I will let you a few seconds, not minutes, to answer this question. Have you used already beam shaping? You may have used double core fiber laser. It's actually a pretty well-known solution now. There are many laser providers which are having such systems. You have an inside core and you have a second core, and you can have energy in both of them, which enables you to have beam shaping. You also have SLMs, which are active systems with a lot of different micro mirrors, which also enables you to have a lot of different beam shapes. You have DOEs, which exist for a very long time now, which are based on diffraction propagation. And you have MPLC, which is a new technology, which we try to develop and to bring to the industry. And you may not have tried beam shaping at all. So please take your time to answer to that survey. And in a few seconds now, I will close the survey. Okay, so I guess that now many of you have already answered the survey. So we will see. You should be now seeing the result. And so what have you tried? Well, the good news is that many of you have already tried beam shaping. 12 of you have already tried different technology, a lot of SLM and double core fiber. I'm not surprised. It's a very mature technology, which are already on the market for quite a long time. But also it's good to know that half of you have not tried beam shaping. So today you will really discover what beam shaping can bring to your process. So let's get back to the presentation now. Thank you all for your participation. And let's now conclude my presentation, with the challenge that we want to take up with laser beam welding. Laser beam welding is a pretty known process now for years, and it's already a huge improvement compared to other technology of welding. You can have automated process which are very repeatable. Laser welding has enabled to have really a better quality. It has also enabled to have faster process, and the depth of penetration is really higher when you do the welding. But still, there are a lot of challenges that have to be taken up regarding laser beam welding, and that's what we want to address with Institut Maupertuis when we develop beam shaping for laser beam welding. We want to have a more robust process. It means, for example, looking at focus shift. We want to weld thicker plates. It means handling higher and higher power. So we are looking at that challenge. We want to enable welding of complex metals, such as copper, which is difficult today to weld with IR laser. We also want to have an improvement in terms of quality, meaning, for example, having less spatter. So we will be addressing all those challenges, and we will present you one solution that we have already developed and tested. And I will let Mathieu now present this solution. The floor is yours, Mathieu.
Thank you, Gwen. Thank you for your presentation. So I'm Mathieu. I'm Technical Project Manager at Cailabs, and I'm in charge of the technical development of high power project. So as Gwen said, I will present the main optical results of the CANUNDA-HP standard platform, and mainly the results of the presentation today, our annular beam shaper for multi-kilowatt laser welding. So here, as you can see, is a photograph of the CANUNDA-HP system. As you might see, we managed to implement the MPLC core technology into a quite standard integrated laser head design. So if we have a closer look to the inner optical beam path, we can see that our design is based on a standard input interface. As you can see, first we start with an LLKD connector. Then, if we follow the optical beam path, you can see that the full design is implemented into reflective optics. So the first optics is a collimating mirror, which is designed and manufactured at Cailabs with homemade and quite efficient water cooling system. So when we follow the optical beam path, then the core technology of the MPLC shaping mirrors are implemented here on 3 shaping mirrors. So the amplitude and phase of the beam are modified through the propagation. And at last, the beam is focused using a focusing mirror. And at the output of the system, we integrate an optical window which protects the whole system from dust or any projection, which might be, of course, replaced in case. And at the output of the system, the target shape is produced in the focal point. So on the laser head and at the output, any kind of accessories might be interfaced. For instance, on the results, you'll see later with Nicolas, cross-jet has been implemented, protective gas supplies as well, and you can implement any other tool on the laser head thanks to different mounting interface and holes on the whole beam shaper. So as you can see on this picture, the beam shaper is mounted on a standard robot, and indeed the commissioning is quite straightforward. There is no optical alignment needed to commission the system when you mount it. You just have to interface it with a dedicated interfacing plate on your robot, connect the chiller and sensors, install accessories, plug the fiber, and then you can operate the system as usual, just like any other standard laser head system. So as you can see, the beam shaping we have implemented for annular ring shape is implemented on a specific laser, here a TrueDisc 16002 with a delivery fiber of 200 micrometer core and 0.1 numerical aperture. But of course, our system can be easily adjusted to any other kind of laser and can be tuned on demand. So on this slide, you see the output shape that is produced by our beam shaper. So the annular shape you see here has an outer dimension of 1 millimeter and an inner core of 600 micrometer. The dimensions of this annular shape have been defined in order to produce a power density inside the ring shape, which is equivalent to a disc of 600 micrometer diameter, and to enable a keyhole in the same conditions of power density. So as you can see on this picture, the homogeneity we reach is quite good because we reach over the circumference of the ring, almost 10% RMS homogeneity over the ring. And the deviation from max to mean intensity along this ring are below plus minus 18%. So on the following slides, you'll see the results, the high power results we got using two kinds of standard high power monitoring system. The first one I will describe are the results we got with the Primus Focus and Power Monitor, which is a tool used to do direct imaging at high power of the beam. And then in the following slides, you'll see the results we got with the beam watch, which is an indirect measurement. The advantage of this first system you see on the picture just below the Primus Focus Monitor is that you have a real and direct image of the beam, and it can be recorded along 120 millimeter, and it enables also to monitor the power in real time. However, this kind of measurement takes for detailed and high resolution data might take up to 1 minute. So effects such as focus shift, which has been mentioned by Gwenn, cannot be monitored. So that's why we used beam watch. You'll see in the next slide. So on this first results we got with the Primus. So you see the real measurements of the annular shape. So here in the center, you see what we got as the waist. And on the left picture and the right picture, what we got at plus minus 3 millimeters. So you see that, in fact, our beam annular shape that is produced is, in fact, some kind of a cylinder, which it's preserved along a very long depth of field, which is also very important to maintain a reliable process. So moreover, here is a more detailed and longer caustic measurement used, made with the same kind of apparatus as you can see with the Primus Focus Monitor. So the full caustic of the system shows that there is no astigmatism at all, and you have a preserved quality of your beam at the output of the beam shaper. So as I mentioned, another tool to monitor the beam at the output is a tool which is called the beam watch. So the measurement is indirect. So you see on this picture the beam which is monitored in X and Y direction. In fact, there is no interaction with any tool. Conversely to the beam watch, the measurement is done by relay scattering. So it enables direct, very fast recording of the beam caustic. So you can follow the waist position in X and Y position within a very high frequency. So here you see the results we got from this measurement at 14 and 8 kilowatts, recorded over about 10 to 20 minutes And you see that the focus shift is maintained below 1 millimeter and is preserved when we thermalize the system. So it shows that the system is really stable at very high power and is very stable, and the position of the waste stays at the very same position. Another important point is that the fact that our system presents stable operation up to 16 kilowatts. And unfortunately, the beam watch had not been able to monitor such high power because the beam watch showed some parasites in the measurement, and that's why we could not record focus shift at higher power than 14 kilowatts. But many kind of process tests have been performed also up to 16 kilowatt for duration longer than 30 minutes. Last but not least, the transmission of the system, thanks to the reflective implementation of the system, is above 99%. So within the uncertainty of the premise focus monitor at ±2%, and it enables so reliable and stable operation over very long duration. So as a conclusion, and before to forward the presentation to Nicolas from the Institut Maupertuis, our beam shaper has a very reliable operation at very high power, up to 16 kilowatts, and shows optical performance, which makes it a system capable of doing quite homogeneous shaping over very long operations. So, Nicolas, I will let you start over.
Yeah, thank you, Mathieu. So, my name is Nicolas. I am a welding engineer at Institut Maupertuis. And for the last part of the presentation, I will talk about all the tests that were carried out in a welding situation at Institut Maupertuis. And before that, I will introduce you to the company. So Institut Maupertuis is a technical resourcing center, which primary mission is to support industry and innovation. To do so, we have expertise in three main processes, which are additive manufacturing, laser beam welding, and friction stir welding. Also, we've worked on industrial robotics, and we developed our own softwares, for example, for path planning and monitoring. Here you can see our technical platform. So, as you can see, we're equipped with high power lasers. We go from 8 to 16 kilowatts, and we work on all the lasers welding applications. So, laser beam welding, hybrid laser arc welding, laser scanner welding, laser cutting, etc. You can see also the wire arc and wire laser additive manufacturing platforms, and finally our friction stir welding platform. Also, we have our own metallurgical laboratory to do some weld seam inspection. So now that you know a bit more about Institut Maupertuis, I'm going to present you all the tests, the welding tests that were carried out with the Cailabs head. So the main purpose of all these tests was to demonstrate the good functioning of the head in an industrial environment, in particular in a welding situation. So to do so, we first did some welding tests on 6mm stainless steel plates, then on aluminum plates, and finally we did some comparative tests with another welding head just to see if there was any difference. For the stainless steel welding, we're using a trailing shield with argon in order to protect the molten pool. And for aluminum welding, we're using a regular tube also with argon. As you can see, we're using our 16 kilowatt laser, 6-axis robot, and also the double core optical fiber. So maybe some of you don't know, but a double core optical fiber is actually a fiber with 2 core diameters. And basically you can choose the laser power distribution between the core and the sort of ring that is surrounded. So the first welding tests that we did were done on stainless steel plates. We could achieve full penetration and also butt weld joints. So for this test, we focused on the three main parameters in regards to laser beam welding, which are the power, the welding speed, and the focal point. So for this test, we fixed the welding speed to 1 meter per minute. The focal point was located 2 millimeters below the surface of the workpiece, and we only investigated the effects of power. As you can see, full penetration could be achieved with a 7 kilowatts laser power, and when we went to 8 kilowatts, we could observe some oxidation. So for the next test, we decided to fix the laser power to 7 kilowatts. Welding speed was not changed, but this time we only changed the focal point position. So we went from 1 millimeter above the surface to 5 millimeters below the surface. And basically for these three configurations, full penetration could be achieved. And so for welding stainless steel plates, we fixed this first parameter, which is basically 7 kilowatts laser power. Focal point is located 2 millimeters below the surface of the workpiece, and the welding speed is fixed to 1 meter per minute. We obtained full penetration on stainless steel plates with a very large and smooth welding seam, and also we could join two plates in a butt weld configuration. Then we did pretty much the same test on aluminum plates, but we could only achieve partial penetration. So again, we fixed the welding speed to 1 meter per minute. The focal point was still 2 millimeters below the surface of the workpiece, and we compared the laser power. So 3 millimeter depth of penetration was achieved with 5 kilowatts, and 4.6 millimeter were achieved with 6 kilowatts. The only difference is that you can see on the micrography that we could observe some blowholes with 6 kilowatts. So for the next test, laser power was fixed to 6 kilowatts, focal point was not changed, and we only compared the welding speed. As you can see, full penetration cannot be achieved because the molten pool will just fall. So we decided to fix the welding speed to 1 meter per minute. And again, we compared the focal point position from 1 millimeter above the surface to 5 millimeter below. And what's interesting is that for these three configurations, we had the same depth of penetration, which is 3 millimeter. And so after that, we also could fix the welding parameter for aluminum, which is 5 kilowatts laser power, focal point located 2 millimeters below the surface, and welding speed is 1 meter per minute. We could achieve 3 millimeter depth of penetration, and also we could join two plates on a butt joint configuration. So after this first test, we decided to do some comparative tests with another welding head that we have at Institut Maupertuis. So here you have all the results for stainless steel plates. The yellow seam is the one obtained with parameter 1, so parameter for the Cailabs head. And then we tried three different technology, I would say. So first one is just a classic spot. The only difference is that we're defocused. Then we used a double core mode, which is basically distributing 50% of the laser power in the core of the fiber and 50% in the ring. And the last configuration is the ring mode. So for this test, we tried to kind of imitate the annular shape, but just using the ring of the optical fiber. As you can see, similar results were obtained with a classic spot and double core mode, but with the ring mode, the surface of the seam was not that good because, as you can see, there is too much strata, which means that if you want to have an annular beam shaping, ring mode won't be very adapted. Finally, we did some comparative tests also with aluminum plates. We compare the classic spot and annular beam shaping, and with good parameters, we could achieve pretty much the same results. So for both welding seam, we have a 5 mm large welding seam with 3 mm depth of penetration. So what we can conclude with this test, well, first, the main purpose was to demonstrate the good functioning of the heads in an industrial environment, in particular in a welding situation, and we could do it by getting full penetration on 6 mm stainless steel plates, also for a butt weld configuration. As you could see, we had a large and smooth welding seam and no major defects on the macrography. Also, we could achieve 3 mm depth of penetration on the 6 mm aluminum plates. And then the comparative test with another welding head showed that with well-adapted parameters, we could achieve pretty much the same results, at least with a classic spot and with a double core optical fiber. And that's it for the tests.
Thank you very much, Mathieu and Nicolas, for your presentation. So now we will somehow reach the conclusion of this presentation. So let's start by summing up what we have said. Well, we Cailabs, we have provided a fully integrated laser head. We have designed it, manufactured it, and it's providing a ring shape based on our technology. This system is actually handling already 16 kilowatt, but we believe that we are able to actually handle even more than that. And actually, we are discussing that already with Maupertuis for future. We have shown no more focus shift or hardly no more focus shift thanks to our reflective designs. And we have demonstrated laser beam welding. And one more time, thank you very much to the Institut Maupertuis. And thank you, Nicolas, for all those tests, which were very important for us. Now it's time for a little video because I like videos. So it should work pretty easily, and it's a good time also for you to ask your questions that you would have while we are looking at this video. So it's our head at Maupertuis, and we're going to have the welding for a few seconds. Don't worry, it's not too long. So it should be now on all your screens, and you can see that we were doing the welding with the protective gas. And that's one of the videos that we made at the Institut Maupertuis as a sum up. And because I like videos. So let's go back to the presentation, and don't hesitate, please, to ask your question now in the chat if you have some. Because it's easier if you ask them a little bit ahead of the Q&A session. I will just say a few words now about what's next. So this system is available off the shelf, so do contact us if you want to have information about that. But what are we going to do in future in terms of more innovation and more new results? We want to have more add-ons. We are working on that also with the Institut Maupertuis. We want to have an online camera to ease the process. We want also to have, for example, more process monitoring captors to have a safer process. We also will be looking to a lot of new process tests. In terms of laser beam welding, we want to look at copper, we want to look at thicker plates, we want to look at gap welding, but we want also to look at other processes like laser cutting or additive manufacturing. And because we will be looking at other processes, we will definitely be looking at other shapes as well. And we want to try all those shapes with the Institut Maupertuis in the next few months or years, probably, and hopefully. So now it's time for the Q&A session. So I think there are a few questions. So we will start with all the questions, and we will share the questions one by one. So the first one is, how is the polarization state of the annular beam? So I guess, Mathieu, you are the right one to answer that one.
Yes, so good question. In fact, in the for this kind of application for welding, we use the widely multi-mode laser input. So in that case, the polarization state, well, it is not would not be defined for such a multimode beam. So if we so far we have not designed. So the system is so that's the answer. So there is no polarization state defined for this annular beam shape. I hope I answered your question.
Okay, thank you, Mathieu. I don't think, Nicolas, you have anything to add on that one. So let's go to another one. This one actually is also very interesting. So what is the minimum beam size you can achieve? Some additive manufacturing processes like SLM or SLS have a focus spot of 60 to 100 microns, sometimes larger, sometimes smaller. So maybe Mathieu, so you are the best to answer to that question.
So in fact, so the input core fiber in our case is 200 micrometer, and as you see, there is a collimating optics and the focusing optics, which are performing, in fact, a magnification factor of threefold. And we have no real limitation on the size of the beam at the output. It's linked to so what is limiting is the PSF of the system. So given an input diameter of the fiber, we might be limited by its PSF. So we have strategies to go below slightly the PSF of the input fiber. But for instance, let's say if you have a core fiber of 50 micrometer, we could of course reach a small spot of 50 or 100 micrometers. So the answer is it really depends on the magnification you want and the core diameter fiber you have at the input, but we have no limitation apart from the PSF of the system.
I will just add one comment on that. We have worked already on additive manufacturing. So we are okay to discuss all that. It's different systems. Yes, definitely they are looking at a different spot dimension, but they're also generally working with different laser power and with very different setup. And it's a very interesting application where there is also a lot to do. Thank you, Mathieu, for your answer. And I will go to the next question. Have we tried with lower power 1 kilowatt range? Maybe Nicolas, you want to comment on the different tests that we have done?
Yeah, for welding, we didn't go to 1 kilowatt, but we tried some welding tests at 16 kilowatts. I just didn't talk about it, but we actually welded 100 millimeter thick aluminum plates with 16 kilowatts, and if I remember well, we had something like 12 millimeter depth of penetration. So we wanted to try 16, but we really didn't try 1 kilowatt.
And maybe Mathieu, you can comment on what we would expect at 1 kilowatt, because I guess that somehow we know how it would work.
Yeah, for sure. We performed characterization with Primus focus and power monitor at different power values. So from the threshold of the laser close to 300 or 400 watts up to so few kilowatts. So the idea was to check if we see differences in the behavior of the beam shaper at different power range, and the answer is that the system remains quite stable, and the cosec measurements were the same at low high power or quite high power.
I guess now we have re-answered that one. So there are three, I can see for now 3 other questions. So the next one, how is the focus shift as a function of the ray range? Not an easy one, and I'm not sure that we have a lot of results on that, but maybe Mathieu, so you can comment?
Yes, so good question. In fact, you are right. I should have mentioned the focus shift not really in millimeter, but respect to the relay length of the laser, not really of the laser, but of the shape we are producing. In this case, on the annular shaping system, the relay length is about 22 millimeter. So we contain the focus shift below 1 millimeter, so it makes something like about 4% of the relay length in terms of focus shift. So yeah, it's better to define the focus shift as a percentage of the relay length, and it's close to 4%.
All right.
So very low, in fact, because so for those who don't know the definition of the relay length, it's the distance at which the beam is multiplied by a factor 2. So it means that we remain at we keep a very stable output shape.
Yeah, somehow it's an excellent question, because 1 millimeter compared to what is always a question. So of course, yes, it's always good to compare to the relay range. And if I understand well, Mathieu, your answer, we would expect probably the focus shift actually to depend on the relay range if we had to do shapes which would be bigger or smaller. Sure. So it might be dependent. The relay length is a constant, so for sure we didn't have tried any other system with other magnification or relay length, but it would be an interesting measurement to perform to see if there is some dependence. Nicolas, because you have a lot of experience on different laser head and on the focus shift issue, maybe you can comment also on that compared to your experience with other heads?
Well, if you want me to tell you what's the main interest of having almost no focus shift is basically that we know that sometimes we have to change the distance between the head and the plates to avoid the focal point position to change, or sometimes you will shoot in some kind of thermal sink for, let's say, 1 minute and wait until the process is stable. So this is, to me, one of the main advantages of having almost no focus shift, is that basically you'll have a very constant parameter. And what I've observed in a welding situation, it's also when you have long distance to weld, this can be a true problem.
Okay, so let's go to another one. It's going to be for you again, Nicolas. In the trials at Institut Maupertuis, have you achieved to improve joint quality welding for aluminium, less irregular, less blowholes, pores, compared with welding with a standard optic?
Well, we didn't make that much welding test on aluminium. We really were focused on stainless steel plates because we actually had really good results. So talking about the blowholes, pores, and stuff, we didn't have a big difference. But like I said, we didn't make many welding tests. So I think this is something we'll have to investigate more.
Okay, thank you, Nicolas. One more question. What is the limitation of the maximum BPP for multi-mode beams? I guess you mean what is the maximum BPP we can take in our system. So I will make a comment on my side and then let Mathieu say more about that. The first thing is that this question can be split in two. With that very system that we have provided to the Institut Maupertuis, we couldn't take huge BPP like, for example, diode lasers, for example. We could take BPPs which were around the TRUMPF laser, and Mathieu will be more precise on that. Nevertheless, I want just to mention that if you change the BPP, meaning generally that you change the laser technology, you still can do beam shaping. It's just that it would have to be another system that we could design for you. We have worked with the laser which have a huge BPP, and we were actually doing top hat with those systems, but we could do also other shapes. We just have to look into details on what is your need exactly. Then Mathieu, maybe you can comment on that question as well.
Yes, I don't have much more to say. In fact, as you mentioned, so this system has been designed for the BPP of the true disk laser, so a BPP of 8. Of course, we can accept wider BPPs, and we just have to slightly re-engineer the collimating input to take higher divergence beams. So as you mentioned, Gwen, generally it's for diode beams. And the maximum BPP we have been dealing with so far is with diode laser for another kind of customer project, which is not a ring shape. And the BPP is, in that case, is 60 millimeter milliradian. So yeah, it's quite huge BPP, and it's based on diode technology laser for other kind of processes, and we manage it as well.
Thank you, Mathieu. I like to answer all questions that we have. So we have more questions. I publish them, but we'll try to be shorter because time is flying. Do we have to plan to go to smaller wavelengths? For instance, a better energy coupling could be obtained using UV light for welding metals. In contrast, at 1 micron wavelengths, a lot of incoming light is highly reflected by metals. I'll try to answer, Mathieu, you can comment then. Yes, we plan to go to wavelengths, or at least I could say that yes, we could go to lower wavelengths. There is, in principle, no limit on that, at least for visible wavelengths. If you want to go in deep UV, it's another question, of course. But basically, it's possible to design systems. It's just that our system are designed for 1 wavelength, so we would have to design a new system if we want to go to other wavelengths. Do you have something to add, Mathieu?
No, it's perfect.
Okay. And now we will finish by the beginning and get back to the person who did ask a question about polarization. I guess somehow our answer was not sufficient. So the actual question is, will the beam shaping system change the polarization state? Mathieu, I'll let you comment on that.
Yes, so good question. In fact, the MPLC, if we do not need to take care about the polarization, so if it's not a requirement, so the polarization state at the output might be anything. So in the case we deal with a monomode laser, let's say, but in the case we ask us to manage to reach some particular polarization state at the output. So not for high power project, but for other kind of application, more linked to the telecom side. So we already managed to handle at the same time the shaping, I mean the beam shaping and the polarization states. But yeah, we would need, I guess, more precision on what you have in mind to control the output polarization state. But the answer is yes, we can manage it. It has to be specified for the specific design of the beam shaper. Yeah. I hope I answered your question.
All right. Anyway, please, if it's not clear enough, do send us an email, and we will try to be clear enough. It's going to be the last question because I mean, we have to end it at one time. But I like that one, so I'm happy to finish with that one. Do you dare 20 to 30 kilowatt laser? We can provide 30 kilowatt fiber laser. 30 kilowatt is big, so it's good that you can provide it. There are not so many lasers working at such high power. And my answer, at least, is yes, we could. At least we believe we could. We haven't tried it yet. Maybe Mathieu, you can comment also.
Yes, I guess that it would be interesting to go higher than 16 kilowatt. And as I mentioned, we already have plans to go higher with Institut Maupertuis. So yeah, we would like to go as high as possible.
Okay, I hope it's answering the question, and I believe it's going to be maybe one of the next steps that we want to address in the next few months and all that. So now I guess we are reaching the end of the webinar. It's really nice to present all those results. One more time, I want to thank you, Institut Maupertuis, for all the work that you have done. And I'm happy that we did present all those results together. It's really nice that we have had so many questions as well. Don't hesitate to contact us if you have other questions on what we Cailabs can provide or what the Institut Maupertuis can provide. And now it's going to be time to say you bye-bye and hope to talk to you soon.
Bye, thank you.
Yeah, bye, thank you.